Hey guys, this is Mrs. Butcher, and this video is over solving exponential functions by finding like bases. So let me give you a problem. Solve for x. And if I said 7 to the x power equals 7 to the 8th power, you would look at that and say, well, it says equals, and the bases are equal, so therefore the exponents have to be equal. So you just set your exponents equal to each other, and you know what x should be. So let's try another one. Here we have 5 to the x plus 1 power equals 5 to the 5th power. So it's supposed to be equal, and the bases are already equal, so we say x plus 1 equals 5. And then we just do baby algebra and solve for x. X equals 4. But what if the bases are not equal, you say? Here I give you 7 to the x power equals 49 squared. The 7 and the 49 don't match. So the trick is, you change them. You change one or both of the numbers so that it is a power with the same base. So I know that 49 is equal to 7 squared. So I'm going to have 7 to the x power equals 7 squared to the second power. Note that you only change the one, or whatever you change, it has to still equal what you started out with. 49 we started out with, we still have 49. We just wrote it in a different way. So if you change it, and you change it to something that's not equal to the same thing as what you started with, then you're going to get the wrong answer. Be sure that you change it to something that is the same. But now we have like bases, so we can say that x has to equal, and then we talked about this yesterday, power to a power, you multiply, so 2 times 2 is 4. X equals 4. So try this one. 5 to the x plus 1 power equals 125 to the 2x power. We should know that 125 is 5 cubed. So I'm going to change the 125 to 5 cubed, and we have 5 to the x plus 1 equals 5 cubed to the 2x. So now that these 5's match, we can set the exponents equal to each other. X plus 1 equals 3 times 2x. X plus 1 equals 6x. Take away the x, we get 1 equals 5x, and that means that x is 1 over 5, 1/5. And that's it. Sometimes you're going to have to change both of them. For example, in this case, 8 is not a power of 4, or vice versa. But we know that both of these numbers are powers of 2, so we're going to have to change both of them. 4 is 2 squared to the x minus 2, and 8 is 2 cubed, and then that's to the x plus 1. So notice that this still equals 4, and this still equals 8. We just rewrote it in a different way so that the bases would match. So now we can say that the exponent 2 times x minus 2, because it's a power to a power, equals that exponent 3 times x plus 1. That's a power to a power. And be sure you remember to distribute. So here we have 2x minus 4 equals 3x plus 3. You have to remember to distribute that to both of these and that to both of these. So now we're just doing baby algebra here. If I took away 2x from both sides, I would have x over here. And if I took away 3 from both sides, I'd have negative 7 over here. So x is equal to negative 7. And let's try one more of these. I've got 1/2 to the 3x power equals 16 to the x minus 3. Now, I could raise 1/2 to something and get 16, or I could think, okay, 1/2 is 2 to the negative 1 power, because that's the reciprocal of 2. So I just changed 1/2 to 2 to the negative 1, and then I keep the 3x power. And 16 is 2 to the 4th power, and then I keep the x minus 3. So now that our bases match, we can just take the exponents. Negative 1 times 3x equals 4 times x minus 3. And do the baby algebra. So we've got negative 3x equals 4x minus 12. And if I took away 4x from both sides, I'd have negative 7x equals negative 12. Divide by negative 7, and I get x equals 12 sevenths. Just leave it as a fraction. 12 sevenths is fine. So now you're asking me, how is this relevant to logarithms? Because yesterday we did just plain old exponent rules, and we did some basic powers because that was preparing us for today. And it's relevant to logarithms when you want to solve things like this. Evaluate without a calculator. Log base 3 of 27 equals x. Now, you're going to have a calculator on the test, so you can check your answer with the calculator, but you have to show me your work on paper. So I have to see you write 3 raised to the x power equals 27. Remember the Ben and Benny thing. 3 to the x power equals 27. So then you say, well, if you didn't have a calculator, you would automatically think, okay, 3 to the third power is 27, so therefore x has to equal 3. Log base 3 of 27 equals 3. Or look at this one. We've got log base 1/4 of 16 equals x. So we're taking 1/4, and I'm putting it in parentheses because it's all to the x power equals 16. And I'm not really sure what I would raise 1/4 to get 16, but I can look at those and I can say those are both powers of 4, because 1/4 is 4 to the negative 1 power. And then we put to the x. And 16 is 4 squared. So now, when I have like bases, I can say, well, negative 1x equals 2, so x must be negative 2. And with all of these, you can check them in the calculator. You can plug this in, and you should get negative 2, but I do need to see your work on the page. Okay, here's a couple of more examples. Log base 2 of 1 over 64 equals x, so we have to rewrite it as an exponential. We would say 2 to the x power equals 1 over 64. And since we don't have a calculator, if you did, you could just plug that in, but you have to think, well, what power of 2 is 1 over 64? So it's 2 to the x equals 2 to the, and then you know since it's a reciprocal, it's going to be negative, and 64 is 2 to the 6th. So that means that x has to equal negative 6. And then this last one, we're going to take the 8, we're going to raise it to the whole x plus 5 power, all of that is the exponent, equals 2. So I can turn my 8 into 2 cubed, and then I have the x plus 5 power equals 2, and that's going to be to the 1 power. It helps to add that in there so that I can say, okay, 3 times x plus 5 equals 1, so 3x plus 15 equals 1, 3x equals negative 14, and x is negative 14 thirds. Like that. So that's why we need to know how to change our exponential problems to have like bases. And that's the end. Have a great night.